Welcome to today's video, which covers section 1.2, initial value problems. So we're going to learn about a specific type of differential equation, which is an initial value problem. We're going to take a look at what those problems look like geometrically as well. And then we're going to take a look at their solutions, and we're going to end with a theorem. So let's start with, of course, what is an initial value problem. So definition at the top, an nth order initial value problem looks like the following. You are solving the nth derivative with respect to n is equal to some function of x, y, y prime, all the way up to y to the power n minus 1. And then when we solve that, we're going to have most likely n different parameters. If you remember from the first video, you're going to have C1, C2, all the way up to Cn. And so in order to find those, you're going to have what we call the initial conditions. So that is subject to y of x naught is equal to y naught, y prime of x naught is equal to y1, all the way up to y to the n minus 1 of x naught is equal to y of n minus 1. So these, as I said, are called the initial conditions. And what you're going to notice is all of the initial conditions are at the same x value. So in this class, we are going to be solving these initial value problems. So generally, we will first find an n parameter family of solutions. And then we're going to use the initial conditions to determine those n constants. Lastly, we will find the particular solution on some interval I that contains that x naught. Okay, so what we're gonna do right now is, now that we know what an initial value problem looks like algebraically, we're gonna take a look at what it means geometrically. Okay, so first looking at a first order differential equation. So first order differential equation is just gonna have dy dx, and then we're gonna have one condition. And so what we would do is we would start by solving this differential equation, and we would end up with a one parameter family of solutions, and that's what we see here. So all of these curves in different colors are all solutions of the differential equations based on different parameters, different of the arbitrary parameters C. So then what we do is we look at which curve goes through our initial condition. And so you'll see that the one in blue is the curve that goes through our initial condition and is contained within the interval I. So what we would be doing is we would first be solving for this family, and then we would be looking at which curve in the family goes through our initial point. Okay, similar idea. If we're looking at, on the right, a second order initial value problem. So this time we have dy dx, we're going up to having the first derivative. Now, because we're second order, we're going to have two initial conditions. So again, we would start by solving for the family of solutions, which is all of these. We then need to find the curve that satisfies both of these conditions. This first condition, again, is the point. So we need the curve that goes through this point. We also need the curve that at x naught has a slope of y1, because that is first derivative is slope. So hence this pink. So we have two conditions that need to be met. We have to go through our point, and at that point, we have to have the given slope. Okay, so let's take a look at the first example where we can see a little bit more of this hands-on. So we're going to consider the differential equation y prime is equal to y. In part A, we are going to verify that y equals c e to the x is a one parameter family of solutions for the equation. So that's what we're going to start with. First thing that we notice is that this is a first order equation, and so we're going to have only one parameter, which is that c. So in part A, if we want to verify, we have y prime is equal to y. So we're going to need to take that y equals c to the x and find the derivative, which is also c e to the x. So then if we substitute y prime and y into our equation, we get c e to the x is equal to c e to the x. So hence we have verified that that is in fact a solution. Now, if we want to draw a few different solution curves, we have to know what e to the x looks like. So e to the x is going to start low. It's going to be exponential growth. So all of these are different c e to the x's, or for different values of c. So there are infinitely many. I've just drawn a few of them. So those are a few different solution curves. Now, though, we want to find the particular solutions that correspond to these 2 points. So if we start with the point 0, 3, and our y equals c e to the x, substituting in, we get 3 equals c e to the 0. C has to be 3 then. So the particular solution that will go through that point 0, 3 is y equals 3 e to the x. And so I haven't drawn that one, but if we had the point 0, 3 right here, our solution curve would look something like this. Again, this is a very poor drawing, but hopefully you get the point of it. So then, on the other hand, if we look at that point 1, negative 2, we get negative 2 is equal to c e to the first. So c then is negative 2 e to the negative 1. So our particular solution then becomes c e to the x. Now, of course, that's not really the nicest way to express that. We instead can write it as negative 2 e to the x minus 1. So that would be the particular solution that goes through 1, negative 2, which I haven't drawn again, but the curve that looks something like that. So this is ultimately what we're going to be looking to do in this course, is taking a differential equation and finding the solution, the general solution, which has one parameter or however many, and then finding the particular one that corresponds to whatever conditions we've been given. So let's take a look at our next example. Okay, example 2, verify that y is equal to 1 over x squared plus c is a one-parameter family of solutions for that equation, then find the solution corresponding to 0, negative 1. Okay, so if we start by verifying, our equation is y prime add 2xy squared is equal to 0. So we have y, which is 1 over x squared plus c. We need to find the derivative. So if we do that, we're going to get negative 1 over x squared plus c times 2x, which can be written as negative 2x, that's squared, over x squared add c, quantity squared. So now if we go back to our differential equation, we get negative 2x over x squared plus c, quantity squared, add 2x times y squared. And we want to know, does that equal 0? So hopefully we can see you get negative 2x over x squared add c, quantity squared, add 2x over x squared plus c, quantity squared equals 0. So we do, in fact, see that this is a family of solutions. What we want to do next is find the family of solutions, or find the actual solution, the particular solution that corresponds to 0, negative 1. So what we're going to do is we are going to substitute that into our equation. So we get negative 1 is equal to 1 over 0 squared plus c, c being negative 1. So our particular solution then becomes y equals 1 over x squared subtract 1. And just to give you a quick review of what this would look like, we're going to have asymptotes at 1 and negative 1. You have a parabola in the middle, and then you have two branches to the left and to the right. Okay, so now one thing to keep in mind here. So this is important. A solution of an initial value problem, we need to consider I, which is any interval, on which y of x is defined, is differentiable, and contains x naught. So if we look back at our function, our particular solution, that y is defined from negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So we've got the defined part. It is differentiable at those places as well, but we need it to contain our x naught. Our x naught in this case is 0. So this is our interval then. That is the interval on which this particular solution is a solution of the differential equation. Okay, let's take a look at one more example on the next page. Consider the differential equation x double prime plus 16x with a family of solutions. As you see, find the particular solution corresponding to those two initial conditions. Okay, so first condition we have is that x of pi over 2 is equal to negative 2. So if we substitute that into our equation, we're going to get negative 2 is equal to c1 cosine of 2 pi, add c2 sine of 2 pi. Well, we know that sine of 2 pi is 0, so we get negative 2 is equal to c1 cosine of 2 pi. So our c1 then is negative 2. Now we go to our other condition. Well, first let me rewrite. We now know we have x equals negative 2 cosine of 4t, add c2 sine of 4t. Okay, so then our second condition is that x prime of pi over 2 is equal to 1. So from our x equation, we're now going to need to find x prime, which gives us 8 sine of 4t, add 4 c2 cosine of 4t. And now we're going to substitute in that condition. So we get 1 is equal to 8 sine of 2 pi, add 4 c2 cosine of 2 pi. Again, we know that sine of 2 pi is 0. So we end up with 1 equals 4 c2. So c2 is equal to 1/4. So our particular solution then corresponding to the two initial conditions is x equals negative 2 cosine of 4t, add 1/4 sine of 4t. So now that we've seen a few examples of what an initial value problem looks like and how to find the parameters associated with a solution, we're going to move on to the two questions that generally arise. So you'll see this right here. When we're solving an initial value problem, before we jump into solving, there's generally two things we want to know. One, is there even a solution? Does a solution exist? And if it does, is it unique? Of course, it would be ideal to us to know these answers before we actually start solving. So for example, if we have this equation right here with this initial condition, we know that y equals 0 and y equals 1/16 x to the 4th are both solutions. Okay, so yes, a solution does exist. So a solution does exist to this equation with this condition, but you can see the solutions are not unique. There are two of them, and you could verify that these are in fact solutions. So the question is, how do we know that a solution exists, and how do we know that that solution is unique? And that's where this theorem comes into play. Let R be a rectangular region in the xy plane, such that x is between a and b and y is between c and d, that contains the point x naught, y naught. If f of xy and the partial of f with respect to y are both continuous on R, then this symbol means there exists some interval contained in AB and a unique function that is a solution to the initial value problem, subject to this initial condition. Okay, so let's take a look at how this applies to this example that we did above. So I know that this is really wordy, and so we're going to take it through this example. So we're going to consider the example from above, which we already said has two solutions. Okay, so first thing is we have our f of xy is equal to xy to the 1/2. We also know that we're going to have to look at the partial of f with respect to y. So the partial of f with respect to y is x over 2y to the 1/2. And so what we're going to notice is that both are continuous when y is greater than 0. And so what we're going to see is from our initial condition, that was not the case, right? Y was not greater than 0, so this theorem didn't apply. So what this tells us is that through any point x naught, y naught, where y naught is greater than 0, there will be an interval centered on x naught, where f of xy has a unique solution. Okay, so for example, if we consider that same equation, but now the condition is that y of 2 is equal to 1, because this 1 is greater than 0, we know that a solution exists and it is unique. Okay, an important note with that. We do not know, though, the size of the interval on which the solution is unique. So we don't know the size of the interval on which the solution is unique, just that it exists. Okay, we have one more example to take a look at, and then we have a few other quick notes to write down. So let's take a look at this example number 5. Determine a region of the xy plane for which the given differential equation would have a unique solution through x naught, y naught. Okay, so first thing that we're going to have to do is get dy dx alone. So really we're looking at dy dx is equal to y over x. So that y over x is our function. So then we're also going to need the partial of f with respect to not x, y, which is 1 over x. And what we are looking for is where are these continuous? Okay, those are continuous everywhere where x is not 0. So unique solution occurs in any region where x is not 0. Okay, so let's take a look at our last few points here. The uniqueness theorem conditions are sufficient but not necessary. That is really, really important. That is really, really important. So, for example, if on this example above, we were looking at the point 0, 0, we cannot say, okay, x is 0, so therefore our solution is not unique. We can't say that. So if we had a region where x was 0, we could not say whether or not there would be a unique solution, because these conditions are not necessary. They're just sufficient. So again, if we had a region where x was 0, we cannot say the solution would not be unique. There could be a unique solution, we don't know though. Okay, next thing to talk about is the difference between an initial value problem and a boundary value problem. Okay, so an initial value problem is going to have initial conditions at a single point. So let's say we're considering this equation. Because there is y double prime, we're going to need 2 conditions. So our conditions might be something like y of 0 equals 0, and y prime of 0 equals 1. So by single point, I guess I mean single x value. So if it's an initial value problem, the initial conditions have to be at the same x value. If it's a boundary problem, our conditions are at different x values. So for the same equation up here, our conditions might be something like y of 1 equals 0 and y of 5 equals 0. Or you might be giving conditions like y of pi over 2 is equal to 0 and y prime of pi is equal to 1. Or you might be given something like y prime of 0 equals 0 and y prime of pi equals 0. So that's the difference. An initial value problem, the initial conditions will be given at a single x value, whereas a boundary value problem, the conditions will be given at different x values. And so that uniqueness theorem only applies to initial value problems. Last note is there's a difference between existing and exhibiting. There's a difference between knowing that the solution exists and actually being able to find it. So this is something that we talked about in the first video. Sometimes we know a solution exists, but we're not actually going to be able to find it. So this uniqueness theorem can help us show that a solution does exist and that it's unique, but it doesn't necessarily mean that we can find it. Okay, so that was our video on initial value problems. Just so that you know what is coming up, in the next set of notes, we are going to be taking a look at some models, how to model physical situations using differential equations. I look forward to being with you next time.